Welcome, ladies and gentlemen, to problem 1. We're looking at functions and their limits. From the sheet that you should have printed from our website, let's go over what we're looking at, and they're asking us to do. Prove that the limit of f of x as x approaches infinity, positive infinity, approaches L. So prove that the limit of f of x as x approaches infinity, approaches L, if and only if the limit of f of 1 over y as y approaches 0 from the right, if that approaches L. Well, now, ladies and gentlemen, when we're doing these proofs, you're going to have to assume that right now that this is true. So right now, at the beginning of our proof, we're going to write, first of all, assume that the limit of f of x as x approaches positive infinity is equal to L. Okay, Jason, John, Mary, Louise, Rhonda, Ed, George, everybody here, you guys got that? Do you follow what I'm doing right now? So right now we have to assume that that is true, that our hypothesis is indeed true. So we're assuming that this is true. Now let's take a close look at our graph of what we're looking at. First of all, we're looking at infinity. Do you know how long or large infinity is? I don't. Nobody really knows. You could have the Star Trek Enterprise. Let's say it went had a speed of 30 warp. So let's say we went warp 30 times the speed of light. Let's say that we could live 400 trillion years and you were going at warp 30, the speed of light, over those 400 trillion years. Well, as we know so far, we know that you would never ever see the end of space, because it would just keep on going on. 400 trillion years from now, you're still going on and you still see the vastness of space. So we don't know where infinity is and how large it is. So now, using that as an introduction to bring it into broaden your thinking. Think about this line going through the vastness of space. Just think of it that way. And that 400 trillion years from now, this line is still proceeding through space and never seeing an end, because wherever end you are, you're just seeing more space. So we don't know where the end is. 400 trillion years from now. Now, what we're going to be looking at, we're trying to prove that no matter what number we pick here, that we're always going to be able to find another number that's a little bit bigger than that. It can even be a nanometer bigger than that, but it can still be bigger than that. And as we're looking at this function, as it's getting close to what we consider this horizontal asymptote, we're calculating the distance between this function and its horizontal asymptote, and we're going to use epsilon to determine the distance between there. We're looking at this length and this length. We subtract those, and the difference gives us the distance between that function. That's known as our tolerance. So like I say, let's see what happens 400 trillion years from now, and I want there to be 30 trillion zeros and a 1 at the end. As long as there's a 1 at the end, that number is not 0. Well, guess what? I can pick an x that when I put that x into the function and then I calculate the distance between this function and that line, that the difference will be equal to the epsilon with the 14 trillion zeros and a 1. But then I can say, well, since we don't know how big infinity is, I could pick something that's just a nanometer bigger, put that into this, and guess what? Now that's going to be a little bit smaller than the decimal followed by 14 trillion zeros. It might end up being 15 trillion zeros, and now I found the number that when I put it into this function, calculate the distance between this function and that horizontal asymptote, it's going to be smaller than the tolerance that I said that I wanted to meet. Because I don't know what infinity is. I don't know how big it is. You could be here for trillions and trillions and trillions of years and never see the end of space. So now, basing that, here's what we're going to say. Now, the next step, looking at our epsilon, our tolerance. Does everybody here understand that? Ralph, George, Maria, Lisa? Good. Well, here's what we're going to say. for each epsilon greater than 0. Remember, there could be 100 trillion zeros after the decimal and a 1 at the end. That number is not 0. It's a number. So for each epsilon greater than 0, well, we can find an x, a large X, capital X, that's greater than 0, such that we can find another number, x, which is greater than that number that we picked to meet our tolerance, and these two numbers are greater than 0. And given that, and given that, we have the absolute value of f of x minus L will be less than epsilon. So that discussion that I went through, that was describing all of that, saying, and excuse me, whoa, I'll just move that out of the way for right now, that I can say let epsilon equal the decimal followed by 14 trillion zeros and a 1. Well, I can pick a number x that when I put it into that function, and when I calculate the distance of this function at that point between that horizontal asymptote, that distance will be equal to epsilon. But then I'm saying, well, since none of us knows how massive, how long, how far infinity is, that I can come to you and say, guess what? I know I can pick a number that's greater than this bar that you found here. It could even be a micromillimeter, that when I put that value into the function, it's going to stretch this point just a little bit closer to that line, so that when I calculate the distance between that point on this line and that horizontal asymptote, the differences will be smaller than the epsilon with the decimal followed by 14 trillion zeros and a 1. It could end up being 15 trillion zeros and a 1. But I just showed that I could do that. So that is what this is saying. So now that I can find a number that's larger than that, that will meet that tolerance. Okay, now, ladies and gentlemen, we are now at the critical step. So what I'm going to ask you to do is to please pause the video, think about what I just told you. So take some time to think it over. Think that through your mind. Expand your mind through space and think about, do I know, does anyone know where infinity is? Because in order to understand the abstract idea, you have to recognize that this line means that this line is going on forever and ever and ever throughout the vastness of space. And none of us knows where the end is. I will be right back. Okay, ladies and gentlemen, I hope that you have had time to copy this down and have thought about what I described to you as far as what's happening with this line throughout space. Now we're at a critical juncture, moving towards closer to proving that this first statement is true. So now, the next thing I'm going to say is, let x equal 1 over y. We're going to let that be so. So now, this is what we know. Well, by substitution, we have the following. In a step-by-step process, we have the following. 1, that the absolute value of f of 1 over y minus L is less than epsilon. And 2, that 1 over y is greater than that capital X, which is greater than 0. And remember, that was just by simple substitution. I said let X equal 1 over y. So by the process of substitution, we have y now is in place of the X. So I'm going to show that here. That in this case, by substitution, I said here we have 1 over y. And now the 1 over y took the place of the X by substitution. So that is one of the concepts that we are using here in this proof. So now, please look closely at what I did. What I'm going to ask you to do now is pause your video. Please copy down what I have done here so far, because I am going to need to erase some of this to continue this on. So at this moment, if you need to, please pause the video, copy this, and think through what I just said and did, and look at the concept that I just used in order to get to this point. Because now we're going to move on to the next step. Okay? Please pause your video, copy the work, and I'm going to erase part of the board, and I shall return. That is exactly what MacArthur told the people in the Philippines. I shall return. Okay, ladies and gentlemen, I am back. Now we're going to move on to the next step. Here is what I'm going to do now. Let me just do a divider here so we can utilize this space, because I want this graph to stay here for right now. Now, the next step we're going to do, we're going to go multiply the inequality. We're going to multiply the inequality by y over capital X. So we're going to multiply this inequality by y over capital X. So let's go ahead and do that. So we're going to show that y over capital X. Now we're going to apply some algebra. We're going to multiply that inequality by that, and we have 1 over y is now greater than x, the capital X, which is greater than 0. Upon doing that, this gives us, notice, the y's cancel. I'm left with 1 over x. So now I have 1 over x. Okay? When I multiply through, this x cancels that. I'm left with y. And anything times 0 is still 0. Okay, am I doing okay so far? Ralph, George, Juanita, Mary, Elizabeth? I'm all right so far? Okay, do you follow what I'm doing so far? So now I just applied some algebra here. All right? Now remember, from the original graph, both of these numbers, the x and the capital X, is approaching positive infinity. So now, as this is approaching positive infinity, this quantity is getting smaller. And now notice as well that when I said let x equal 1 over y, y is now equal to 1 over x, and since x is also approaching infinity, this is also getting smaller, because now remember that we had, by interchanging the places, that y is now equal to 1 over small x. Okay? Now the next step is, what I'm going to say is let capital X, let delta equal 1 over capital X. Then we have this is what we have. Delta is greater than y is greater than 0. Now let's see what that means to us graphically in relation to this. This is controlling that. Alright, so now let's take a look at the number line. Well, putting this on a number line, here's what we have. Here's 0. And now y is here. And delta is somewhere here. So that is what we have so far. Delta is greater than y, which is greater than 0. Alright? Everybody here have that? Are there any questions? Do you have any questions? Alright, take a look at this. Look at what I did so far. I'm going to give you a chance to please pause the video right now and just consume this. Copy this. Think about what I said. That remember that we still know that in this case bar x is approaching positive infinity, and we know that that little x is also approaching infinity as well. It's squeezed between here. It's like two rings on an infinite line, and they have the same poles, magnetic poles. They repel each other. So as I'm pushing the x, it's also pushing that small x along the line, trying to reach infinity throughout the vastness of space. Okay? So think that over. Pause the video. Think about that. Take some time to think about that. And this line is going through the vastness of space. None of us knows how long, how in depth space is. We have no idea where infinity is. As of right now, we can say that we don't think that there is any end to space, that we could be going through space 400 trillion human years, and 400 trillion human years later, going at warp 30, and even if we did a hyperspace, we still would not reach the end of space. We still see vastness of space. So we have no idea where infinity is. So I want you to expand your mind, close your mind, and see yourself traveling through the vastness of space while these values are traveling along that line through the vastness of space. Pause your video. Think about that. Okay, ladies and gentlemen, please continue to ingest that. Now, here goes the next step. Next, we are going to use the squeeze theorem. We're going to use the squeeze theorem. And here's what's going to happen, ladies and gentlemen. As delta approaches 0, well, by the squeeze theorem, I'm going to abbreviate that, by the squeeze theorem, y is also going to approach 0. And that is what we needed to show here, that y is approaching 0 from the right. So everything here is sliding to the right. That's sliding to the right. That's sliding to the right. So as this is getting smaller, approaching 0, the y is sandwiched between delta and 0. So this is approaching 0, and this is sandwiched between 0 and this. By the squeeze theorem, y is also approaching 0. Think about that. That is what the squeeze theorem tells us. So we're almost there. So what I'm going to ask you again to do is to pause the video. Please copy what I have here so far. I'm going to erase this part, and we're right here at the end of our proof. I will be right back so I can clear this and complete this particular part of the proof. Okay, ladies and gentlemen, we are here. Well, by this number line and by using that, notice everything is approaching 0 from the right. Guess what? We have just proven that the limit of f of 1 over y as y approaches 0 from the right is equal to L. We have just proven that. So this wraps up the proof. We have just proven that by here. So this wrapped up our proof, and this allows us to conclude, yes, that the limit of f of 1 over y as y approaches 0 from the right is indeed equal to L. Again, this is on my website, so anything that's on there, if you have questions about the reasoning and about the abstractness of the line going through space forever and ever and ever and ever and ever and ever, if there's something here that doesn't quite click, please email me. I'll be glad to communicate with you discussing this particular problem, or you can call me and I'll be glad to discuss this problem with you. Thank you for joining me. Please make sure that you copy this work. Excuse me. Woo! Woo! Pause your video. Please copy this work. Thank you for joining me. And we're going to take a look at part B. I will be right back. Thank you so much for your time.